So here's some of the subtopics that we covered. Going into the exam, I can either tell you which technique to use, or I can not tell you the technique to use for integration. So these are purely just integration-based questions, and they could require any of those dot points. So it's just kind of going, what are the clues or hints to figure out which of the dot points are they asking us to use? So I might just test you guys, see if you can figure out which is which. So this one here, what do you think? What is the technique we use to solve this type? It's got y times y as a function inside a power. So this is substitution, so letting u equal to something. So first hint, if there's a power means, and there's no trig and there's a power, that means substitution. So the bit inside the power. Now this is a particular type of substitution. So once you figured out its substitution, you need to figure out, is the derivative present? Can you guys see a derivative present of the thing that you let u equal to? No. So this is called linear substitution. So we're rearranging to let the thing outside the power be isolated. So you want to get y by itself. So you bring the 3 over like that. So that's the second step, is the derivative present. Alright, and then you follow through. So usual substitution steps. Du dx or du dy, because it's in terms of y. And then once you've solved that, you guys should know the steps from here. Sub in for dy, sub in for y's, and then integrate for du. And then sub y back in. Alright, what about this one? So there's a sign in there. So that could be a hint. We need to use a trig identity. What do you guys think? The derivative is present. So there's a function, a squared plus 14a, and it's inside another function. It's kind of like the chain rule for integration. So there's a function inside the sign, and we can also see the derivative of that function is present. So we just let u equal to the function and then follow the same steps as before. So du dA, rearrange, sub back in, and solve. Alright, what about this one? Yep, substitution, and although the derivative's not present, so if you did du dx when u is 5x minus 3, the derivative is 5, but you can still do this function because it's a constant. So that's another, it's almost when the derivative is present. But this time the derivative is a constant, so it's not a big deal. So you follow those same steps. What about this one? This is one of the inverse integrations. So if there's on the bottom of the fraction, so there is a power x squared on the bottom of the fraction, and it's adding to a number that could be squared as well. So this is the form of tan. So this is a special case, this is an inverse tan. Alright, what about this one? Cos squared x over 4. Yep, so if you ever see the cos, sine, or tan being squared or cubed or to the power of 4, this is where we're trying to eliminate that power. I don't know if you ever remember trying to eliminate the squared. Here we go. So here's a whole bunch. So if you've got cos squared, you're trying to eliminate the squared. So turning it into just regular cos. Eliminate trig powers. What about this one? X sine x. So again, we have a trig function present. There's no power, so there's no trig identity. And the derivative isn't present. So we have a special case. We have a function times a function, x times sine x, which is a trig function. So when there's two functions being multiplied, this is called by parts, and most of you got it, yeah, by parts. Here's another one. We've got a fraction. So this is similar to the fraction we did here. So there's a quadratic in terms of a trinomial. So you could factorize the bottom and then use partial fractions. So turn the bottom quadratic, whatever it is, into two separate fractions, like that, using partial fractions. Yes, there's also the derivative present. So some of you figured that out. I was wondering if you would spot that. So you could also use substitution. Use the substitution method. And that would eliminate the top row when we sub back in. So this would become du over 2x minus 3, and that would eliminate the top row. Here's another one. Yep. So it's going to be either inverse sine or cos, because like I said before, if there's a squared on the bottom, like that, it's possibly going to be sine, cos, or tan, and there's a square root this time. So it's going to be sine or cos. The difference between sine or cos is there's a plus up the top, so it's going to be sine negative 1. And then we come to the applications. So these applications, I think there's 3 main applications. Area and volume is one application. So you can find the area. The area is the integral of the top function, let's call it f of x. Minus the bottom function, whatever it is. So a sketch is usually helpful because it tells us which one is the top function, which one's the bottom function. And it also tells us the intercept points, if they don't tell you the intercept points. Does anyone remember how to take the area and turn it into a volume of revolution? I think it's just one extra step. So here's your function y equals x, and to get the volume you multiply by pi and square the function. Then we have Simpson's rule. This example, it's going from 0 to 1 for the x values. So the first step is drawing the table for x and y's. So there's 4 strips. So there's 5 numbers for x, all the way up to 1. So you essentially divide, and you can figure out what these are by doing 1 minus 0 divided by 4. So each x value goes up by a quarter. And then you sub that number into there to figure out the y's. So Simpson's rule is useful if it's a complicated integral. It's an integral which is not easy to do. And then we use Simpson's really big rule, which is on your formula sheet. Area equals. Yeah, there we go, Simpson's rule. So subbing in the w figured out, quarter, and then subbing in each of the y values to figure out an approximate integral. So that was quite a quick crash course of topic 4.